Welcome to the lecture on energy management, which is adapted from Chapter 4 of the Airplane Flying Handbook 2021. The FAA has embarked on a new approach to teach management of airspeed and altitude using an energy-centered model. These are the objectives, motivation, and key takeaway points contained in this lecture. Now let's get started. The total mechanical energy of an airplane in flight is determined by the sum of two factors. Potential energy, which is related to true altitude and is equal to mass times gravity times height. This is the energy of position. Kinetic energy is related to indicated airspeed and is equal to 1/2 the mass times airspeed squared. This is the energy of movement. As the airplane climbs, it gains potential energy, which can then be exchanged for kinetic energy. Similarly, the pilot can trade airspeed for altitude. Proper management of these two variables along with thrust assure safe and efficient flight. In an airplane, the engine provides thrust, which is used to increase total energy to the system. Drag opposes thrust, which is divided into two types, parasitic drag and induced drag. Energy flows continuously in the airplane as it gains energy from thrust and loses it through aerodynamic drag. Specific excess power reflects the rate of energy change and is a direct function of thrust and drag, given as thrust minus drag multiplied velocity, all divided by weight. Now let's review the effects of parasitic and induced drag on total drag imposed on the airplane at different airspeeds. The L/D max curve describes the effect of induced and parasitic drag on an airplane at varying airspeeds. At the bottom of the curve is our best glide speed. Note, when we talk about total drag, we're also referring to the thrust required to maintain a specific airspeed. In other words, they are equal in magnitude, but opposite in direction. For velocities greater than L/D max, parasitic drag is the main component of total drag. Below L/D max, it is induced drag which contributes most to the total drag. Next, we will look at thrust and power over varying airspeeds. Beginning with thrust, we see the highest thrust is at the lowest airspeed since the propeller is at a high angle of attack. As airspeed increases, the angle the propeller blade makes with the oncoming relative wind decreases, which in turn decreases its angle of attack, and thus thrust decreases. The speed at which you have the maximum angle of climb is where the difference between the thrust available and the total drag is greatest. That is Vx. This is the speed at which you have the greatest gain in height over the shortest distance and is used to clear obstacles near the departure end of the runway. Power is defined as work done per unit time, so you can compute power required by multiplying your total drag or thrust required by your airspeed. That is, power required equals thrust required times airspeed, which is measured in horsepower. Next, plot a power available curve, which is thrust available times airspeed. The airspeed which produces the largest difference between power available and power required yields the best rate of climb and is used for most normal takeoffs. Now let's begin to talk about the interplay between thrust, drag, airspeed, and altitude on the energy state of the airplane. This graphic displays some of the typical energy interactions which occur. The balance or imbalance between thrust and drag determines whether the total mechanical energy to the system, stored as altitude and airspeed, increases, decreases, or remains unchanged. In the first two examples, the airplane has more thrust than drag. The pilot can use this excess thrust to add altitude while maintaining a constant airspeed, or use the excess thrust to increase airspeed while maintaining level flight. In the next two cases, the airplane has less thrust than drag. The pilot can expend the stored altitude to descend at a constant airspeed, or trade airspeed in order to maintain level flight. In the final two examples, thrust and drag are equal. The pilot can maintain level flight at a constant airspeed, or If they wanted, they could climb at a reduced airspeed. A third option not shown is to descend at an increased airspeed. In all three instances, there is no net change of total energy, only redistribution between potential and kinetic energy. The idea of how energy flows during flight can be simplified by the energy balance equation. This energy-centered approach modifies the old adage of pitch for airspeed and power for altitude. Instead, we should think in terms of pitch plus power controls energy state. The throttle is the total energy controller, and the elevator is the energy distribution controller. Through the coordinated use of throttle and elevator inputs, the pilot controls the airplane's energy state. Putting these ideas together, we can look at the power requirements versus power available as airspeed changes. Also depicted is the relative excess power available, which can be used to establish a constant airspeed climb or maintain a level bank turn with increased load factor. More on this in a few minutes. The minimum power airspeed, also known as maximum endurance airspeed, marks the division between the front side and the back side of the power curve. This is not the same as best glide speed. Also notice how on the back side of the power curve, it takes relatively small change in airspeed to gain considerable excess power. Let's dig a little deeper on what's going on. We just saw how excess power can be used to manage the airplane's flight path and/or airspeed. Now let's see what happens as the airplane moves along the power curve. When cruising at a high airspeed on the front side of the power curve, the angle of attack is low and there's little excess power available from the engine. Applying back pressure to the yoke will cause a brief energy exchange climb, causing the airplane to lose airspeed. Now as the airplane slows, the total drag, which is mostly parasitic, decreases. As a result, there is less power required at this new flight condition, resulting in an excess power being available. This excess power can be used to continue a constant airspeed climb or a level turn while maintaining a constant airspeed at an increased load factor. Let's now look at what happens on the backside of the power curve where the airspeed is slow. In this flight condition, the angle of attack is high and there is little excess power available due to the very high induced drag. Applying forward pressure to the yoke will cause a brief energy exchange descent, causing the airplane to gain airspeed. As the airplane speeds up, the total drag, which is mostly induced, decreases and there is now excess power available. As we saw in the previous slide, this excess power can be used to continue a constant airspeed climb or perform a level turn while maintaining a constant airspeed at an increased load factor. Now let's look at a practical example from William Kirchner's book, The Flight Instructor's Manual. Suppose the airplane is well on the backside of the power curve, just about to touch down. The airspeed is just above the stall. When a cow or car moves onto the runway, the pilot opens the throttle all the way. They have to move the wheel or stick forward to climb. If they keep the wheel back at the near stall condition, the lack of excess horsepower will not allow them to climb. The best rate of climb speed, for example, is 80 knots. They have to push the wheel forward to get that value. Now let's look at the animation, which illustrates the same idea. Now let's take the knowledge we've learned and apply it to real-world flying. By understanding the rules of energy control, we can anticipate and mitigate problems related to mismanagement of power, airspeed, and altitude. At the beginning of this lecture, a comparison was made between an airplane's energy and a roller coaster. Recall the total energy state of the airplane is comprised of its potential and kinetic energy. So an airplane at a given altitude and airspeed has a total specific energy given as height plus 1/2 velocity squared divided by the gravitational constant. An altitude speed map can be constructed to illustrate how an airplane with a specific energy changes along for a given height line. This energy map demonstrates theoretically how an airplane can move along specific energy height lines by trading altitude and airspeed back and forth without changing the total energy. For instance, at the energy height line of 11,000 feet, the airplane could theoretically reach a speed of 350 knots at an altitude of roughly 5,800 feet. Conversely, the maximum height it could attain would be 11,000 feet with zero airspeed. In reality, the airplane would stall before. Nevertheless, the altitude airspeed map is useful in understanding how the two are interrelated. However, in order to cross to a higher energy height line, power must be added, and to move to a lower height line, the total energy must be decreased. In this example, let's look at the energy height line of roughly 6,450 feet. The specific energy anywhere along that line will equal 6,450 feet. Within the limits of estimating the exact numerical values from the graph, at point A, the airspeed equals 100 knots and the current altitude 6,000 feet. Solving the equation for specific energy at A, we get 6,444 feet. At position B, the altitude is 4,000 feet and the airspeed is approximately 235 knots. The specific energy calculates to 6,449 feet. The key point is, for a given energy height line, the pilot can manipulate the elevator and trade airspeed and altitude without adjusting the throttle. However, in order to move to a different height line, the total mechanical energy must be increased or decreased. This is accomplished through manipulation of thrust and drag. We just saw how the elevator can be used to move along height lines, but it can also be used to reduce the total energy of the airplane. This graph illustrates the power requirements for an airplane experiencing increased load factor. Consider what happens in a level turn. As the pilot banks the airplane, elevator back pressure must be increased in order to maintain level flight. This in turn increases load factor. The byproduct of increasing the angle of attack is an increase in induced drag, which steals energy from the airplane, causing it to slow. In order to maintain the original airspeed, the pilot must add power. Another observation from this graph is the decrease in excess power available as load factor is increased. Recall specific excess power is given by thrust minus drag times velocity divided by weight. Using this equation, we can develop specific excess power contours which can be superimposed on the energy map. Note the outer contour represents the envelope where there is no excess power available. More on this later, but now let's begin our discussion of the three basic rules of energy control. As we saw earlier, moving along a line of constant energy from position 1 to 6 or 7 is accomplished by the use of the elevator only, that is, the redistribution of energy along a given height line. However, moving the airplane from position 1 to, say, position 2 or 3 requires a higher throttle setting to increase the total energy. The elevator is then used to distribute this excess power to climb to a higher altitude at a constant airspeed, or alternatively, maintain level flight with increased airspeed. Moving to position 4 or 5 requires a reduction in the total energy by decreasing the throttle, and the elevator again used to distribute the energy. Now let's look at each of these rules individually. Rule 1. If you want to move to a new energy state demanding more total energy, then increase throttle so thrust is greater than drag. Then adjust pitch attitude with the elevator as needed to distribute the energy being gained between altitude and airspeed. For instance, to climb at a constant speed, add throttle and pitch up just enough to maintain the desired airspeed. To accelerate at a constant altitude, add power and gradually pitch down just enough to maintain the flight path. In either case, upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. Rule 2. If you want to move to an energy state requiring less total energy, then decrease the throttle so thrust is less than drag. Then adjust pitch attitude with the elevator to distribute the total energy being lost between altitude and airspeed. For example, in order to descend at a constant airspeed, you would reduce throttle and pitch down just enough to maintain the desired airspeed. If you wanted to slow down, Say on the downwind leg of the traffic pattern, you would reduce power and gradually pitch up just enough to maintain level flight. In either case, upon reaching the new desired energy state, adjust the pitch attitude and throttle setting as needed to maintain the new path speed profile. If you want to maintain the same total energy, you can trade airspeed for altitude or vice versa. To accomplish this, use the elevator and adjust pitch attitude to exchange energy between altitude and airspeed. For example, to trade airspeed for altitude, pitch up. To trade altitude for speed, pitch down. Upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. Now let's consider two scenarios which illustrate major risk factors associated with mismanagement of energy. In the first case, the pilot has descended below the desired glide slope while on final approach to land. What should they do? The best response will depend upon the total energy state of the airplane. We will also discuss in more general terms how to respond to unwanted deviations involving unintended altitude and airspeed excursions. In the second scenario, the pilot is experiencing unintentional, irreversible deceleration and/or sink rate, causing depletion of their mechanical energy, with little or no available excess power for a given flight condition. What should be their course of action? We will discuss how to manage these and other situations over the next several minutes. Let's begin with how to correct energy management errors. In the event of an unwanted deviation in vertical flight path and airspeed, the goal is to return the airplane to its target energy state. Although the pilot's intention is to correct altitude and airspeed deviations, they should think about the situation as managing problems of energy. In other words, establishing the appropriate kinetic and potential energy states. Luckily, we have two instruments on the flight deck which can help us. The airspeed indicator provides us with information about kinetic energy, which is related to speed, and the altimeter tells us about potential energy related to height. As we will see, there are two types of energy errors: total energy errors and energy distribution errors. Monitoring the altimeter and airspeed indicators allows the pilot to distinguish between these two types of energy errors. Consider A as the ideal for a given phase of flight. In the case of total energy errors, the airspeed and altimeter move in the same direction. For instance, high total energy is associated with high airspeed and high altitude. Conversely, low total energy errors are associated with low airspeed and low altitude. On the other hand, when a pilot encounters energy distribution errors, the altimeter and airspeed indications move in opposite directions. The following exercise will help us understand how deviations in airspeed and altitude can affect our total energy and what steps can be taken to correct the problem. This matrix illustrates 12 possible energy scenarios. While at first it seems complicated, using our knowledge of energy management, we should be able to find the correct answers to each of the problems. Practically speaking, when flying, it's the pilot's responsibility to be aware of the airplane's energy status so appropriate corrections can be anticipated or made in a timely fashion. Let's begin. In this first example, there is no deviation. The energy of the airplane is where the pilot wants it to be. Therefore, no action is required. Here, the total energy is on target, but the airspeed and altitude are moving in opposite directions. This is an energy distribution error. An example could be an airplane which is high on final but slower than ideal. To correct this, trade altitude for airspeed with forward pressure on the elevator without adjusting power. This is another example of an energy distribution error wherein the airspeed is faster than desired, but the altitude is lower than ideal. The pilot should add back pressure to the elevator and exchange airspeed for altitude to re-establish the ideal flight path airspeed combination for the given phase of flight. In this case, the total energy is high due to increased altitude over what is desired, but the airspeed is on target. The pilot must respond in a way to keep the airspeed constant while reducing the total energy so they can descend. By reducing the power and using appropriate elevator back pressure, they can shed the excess energy and descend to the desired altitude. As always, upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. Imagine flying along when significant turbulence are encountered. The pilot would like to decelerate to maneuvering airspeed to avoid overstressing the airplane. The altitude is on target, but the airspeed is higher than suitable for this flight condition. The correct response would be to reduce power and apply appropriate elevator back pressure to maintain level flight as the aircraft slows to the desired airspeed. By reducing power, the total energy decreases to allow aerodynamic drag to slow the airplane. Upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. Now the pilot faces the dilemma of being too high and too fast, resulting in excessive total energy. They must slow down and go down. First, reduce throttle significantly to decrease the total energy and apply back pressure to allow the airplane to gradually decelerate. As the correct airspeed is achieved, begin to descend to the desired altitude. If level off is required, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. On the other extreme, this problem can be compared to an approach to stall at safe altitude. The low airspeed represents a high angle of attack and thus very high drag. By reducing the angle of attack, the pilot can significantly decrease the induced drag and thus increase airspeed. We can then trade the excess altitude for airspeed. The appropriate response then is to apply forward pressure on the elevator control, reduce the angle of attack, and gain airspeed at the expense of altitude. Upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. We now begin discussing states of low total energy. In the present case, the airplane is at the desired altitude but is too slow. The pilot should recognize this and respond by increasing the total energy with throttle. The airplane may have a tendency to pitch up, which the pilot should address by adding forward pressure on the elevator. Then, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. This is another example of low total energy, but this time the airplane is lower than desired while flying at the target airspeed. The pilot once again must introduce power to increase the total energy and use the elevator to maintain the current airspeed as the airplane climbs. Then adjust pitch attitude and throttle setting as needed to maintain the new flight path airspeed profile. We're now entering the more dangerous energy states where early recognition and correction is extremely important in order to avoid a potentially catastrophic event. Here, the pilot finds themselves at a low altitude and slower than desired airspeed. Imagine being low on final and below your final approach speed with obstacles at the approach end of the runway. What would you do? Since the total energy is very low, power must be added. Forward pressure on the elevator should be applied to avoid further slowing of the airplane. Allowing the airplane to accelerate will provide the pilot the option to recapture the glide path at a more desirable airspeed or climb as necessary. The next condition is risky. The pilot has the desired altitude, but a very low airspeed. In this configuration, there will likely be considerable induced drag, which should be mitigated. If there is altitude available to trade, then consider initially gaining some airspeed at the expense of altitude. Add full power and establish a climb when there is sufficient energy available. This is the most dangerous energy state for a pilot. Options may be very limited and prompt action is required to avoid disaster. Imagine a group of deer meander onto the runway. A go-round is indicated, but you're very slow and only a few feet off the ground. Apply full throttle while avoiding a rapid pitch-up attitude which would increase drag and impede a climb or possibly induce a stall. In this situation of high power and high angle of attack, anticipate considerable left turning tendencies and respond with adequate right rudder. As energy is gained, use aft elevator pressure to establish a climb attitude of Vx or Vy. Our final discussion will address the situation of irreversible deceleration and or sink rate. During normal flight, there are many instances where negative energy rates are desired. For example, decelerating at a constant altitude or descending at a constant airspeed. However, circumstances may arise where the airplane is unable to produce enough power to safely climb above terrain and or prevent sinking. Let's look at an example. This case study is produced by the AOPA Air Safety Foundation and can be found on the web by searching Into Thin Air and AOPA. It highlights the sobering consequences of not fully anticipating the dangers associated with high terrain and high density altitude flying. This event is eerily similar to the example used in this edition of the Airplane Flying Handbook. We encourage you to watch this presentation from the AOPA. The example used in the current edition of the Airplane Flying Handbook is as follows. A pilot of a normally aspirated twin-engine airplane departs out of Rocky Mountain Metropolitan Airport on a nice summer morning and flies to Aspen County Airport. The pilot enjoys the scenery around Aspen, eats lunch, and decides to return home in the early afternoon when the temperatures are still quite high. The pilot departs Aspen off runway 33. At full throttle, the airplane takes longer to accelerate, but rotates at the normal speed. The pilot pitches for a normal climb attitude, retracts the gear, and initiates a climb. Soon the pilot notices the airplane isn't performing as expected. They check to confirm the gear is up and adjust the mixture to try and get a little more power. The terrain is rising, and the pilot gradually pitches up and the airplane starts losing airspeed. Soon after, the airplane quits climbing and the stall horn begins to sound. The airplane has encountered an unintended deceleration and impending sink rate, which could possibly become irreversible. Let's examine more closely in terms of energy management how this happens. So how does this situation occur? Recall our power required versus power available curve from earlier. At sea level, there is plenty of excess power throughout most of the airspeed range of the airplane. However, at 8,000 feet, the engine is unable to produce as much power. At the lower end of the airspeed envelope, position 2, where induced drag is rising exponentially, the plane is unable to climb as there is no excess power available at this altitude. Note at sea level, there would still be excess power to climb at the same airspeed. If the pilot increases their pitch, the airplane slows further to position 3 and is at risk for stall. With rising terrain below, there may not be sufficient altitude to recover before impacting terrain, trees, or other obstacles. Using the energy map and specific excess power contours to discuss the same situation, we can follow along as the airplane moves between and along energy levels. The airplane is at full power. At position 1, the pilot becomes aware of rising terrain. As there is still some excess power available, they can climb to a higher energy level from roughly 8,000 feet to 9,500 feet in this example at position 2. The terrain below continues to rise up and efforts to climb further are not possible as there is no excess power available. Efforts to try and climb by increasing the angle of attack only serve to further slow the airplane to position 3 where the stall horn sounds. The pilot is now faced with a very difficult situation, finding themselves in a near stalled condition and relatively low to the ground. How should you respond? Proper energy management is the key. In this situation, we need to move the airplane to a place on the energy map which will provide excess specific power to begin a climb away from the ground. Since the energy's thrust is at maximum, you must reduce drag in order to give the airplane the excess specific power to allow it to climb. We accomplish this by lowering the nose and trading some altitude for airspeed. Once the airplane accelerates to an airspeed where specific excess power is greater than 0, it can begin to climb. Depending on how quickly the terrain is rising, you may choose an airspeed for best angle of climb or best rate of climb. Your next decision would be whether to continue on or turn back toward lower terrain, land, and reassess the situation before trying again. Note you do not have to be over high terrain to encounter this type of scenario. For example, an unstable, slow, and low approach to landing, or high drag configurations during a go-round can lead to similar energy problems. In all cases, be aware of your current flight condition and compare it to the ideal for the phase of flight. Continually monitor your altimeter and airspeed indicators to obtain information regarding the energy state of your aircraft. This will help determine what options you have to manage the total energy of the airplane to achieve the desired result. In conclusion, when managing your airplane's energy, your goal is to detect, correct, and prevent altitude and airspeed deviations through the proper use of throttle and elevator inputs. Thanks for joining us, and remember to fly smart and stay safe.